Let's work out some problems in trying to find the local maximum and minimum values of functions. So for example 1, we're given the function x squared plus y squared minus 2x minus 6y plus 14. So let's find the local maximums and minimums. So first, we have to find any critical numbers. So again, the critical numbers are the values where our partial derivatives are simultaneously zero, right? So we'll start off by computing the partial derivative of f with respect to x. That will be 2x minus 2. Partial derivative of f with respect to y, that's 2y minus 6. We'll set these guys simultaneously equal to 0, so we have to figure out when 2x minus 2 is equal to 0 and where 2y minus 6 is equal to 0. And again, we have these guys, we need both of these guys to be satisfied simultaneously. In this case, it's a piece of cake. Because that first equation only has x's, it's clear that x has to be 1. Because that equation only has y's, it's really clear that y has to be 3. So 1 comma 3 is a critical number. And potentially where our function might have a local max or local min. For our next step, we'll go ahead and compute our formula for d. And again, d was equal to the second partial derivative with respect to x times the second partial derivative with respect to y minus the mixed partial quantity squared. And we're evaluating all of these guys at the critical number of 1 comma 3. In this case, the partial derivatives are really nice and easy. So we have the first partial derivative with respect to x. If we take the partial derivative of this guy with respect to x again, f of xx would give us 2. For fyy, it's taking the partial derivative of this guy with respect to y, so that's another 2. Minus, here's the partial derivative with respect to x. If we took the partial derivative of that guy with respect to y, it would be 0. Square that gives us a 4. And this guy, 4, is greater than 0. So we have that 1 comma 3 is a place where we either have a local max or a local min. To determine which of these guys we have, we'll look into the second partial derivative at 1 comma 3. That guy is equal to 2. And because 2 is greater than 0, we have that this guy, our function at 1, 3 is a local minimum. Now, our final answer should be the value of f1 comma 3. So again, our function is that guy there. Well, where did it paste it? Oh. And if we plug in 1 comma 3, 1 for our x's, 3 for our y's, we get 4. So your function has a local maximum at 4 at the point 1 comma 3. Oh, excuse me, local minimum at 4. Yeah, something sounded funny. So local minimum of 4 at 1 comma 3. We can verify this graphically. If I were to graph out our function on GeoGebra 3D, it's a paraboloid. And notice that down here we have a local minimum. And that guy should be at the point 1 comma 3 comma 4. And in fact it is. So if you observe this graph here, the point that we have just found is 1 comma 3 comma 4. Let's continue this with example 3. In example 3, we're asked to find the local maximum and minimum values of the function fxy equal to x to the fourth plus y to the fourth minus 4xy plus 1. So find the local max min of your function. And we'll start out just the same. Look into finding our critical numbers. So we have to take the partial derivatives of our function with respect to x. That's 4x cubed minus 4y. And then the partial derivative of f with respect to y, that's 4y cubed minus 4x. And this guy has to be 0, and that guy has to be 0 simultaneously. So what we really have is a system of equations. So I can take that first equation and divide every element by 4, and that second equation and divide every element by 4 to get a system of equations that's a little bit easier to work with. And here we could use the substitution method and solve for one of the variables in one equation and plug that information into the other equation. In particular, from the first equation, I could say that y is equal to x cubed, and take that information and plug it into the second equation. So again, from equation 2, I'm replacing y with x cubed. So I get x to the 9th minus x is equal to 0. I can factor out an x and have left behind x to the 8th minus 1 is equal to 0. Here I have a difference of squares, and I can break that up into x to the 4th minus 1, x to the 4th plus 1 equal to 0. Here I have another difference of squares, and I can write that guy as x squared minus 1, x squared plus 1, x to the 4th plus 1 equal to 0. Here I have another difference of squares, so then I am ultimately left up with x minus 1, x plus 1, x squared plus 1, x to the 4th plus 1 equal to 0. Whew. So these factors give me some insight about what the zeros are for this function. This lone x in the back end here tells me that x is equal to 0. This x minus 1 factor tells me that x is equal to 1. This x plus 1 factor tells me that x is equal to negative 1. I potentially might have another solution from here, x squared plus 1. What are the zeros of that guy? Well, if you set x squared plus 1 equal to 0, then you have that x squared is equal to negative 1. And then when you take the square root, can you take the square root of a negative 1? Nah, you get some imaginary numbers. So this guy doesn't contribute any real number solutions. And for the same reason, this guy doesn't contribute any real number solutions. So you have just 3 values of x satisfying that equation. For these 3 different values of x, we have to find the corresponding values of y by plugging these values of x into either the first equation or the second equation. From this first equation, we were able to take that guy and write it as y equal to x cubed. So this really is the first equation, y equals x cubed. If x is equal to 0, then what is y? Well, y equals x cubed, right? And so y equals 0 cubed, so y is equal to 0. So when your x is equal to 0, your y is equal to 0. So 0, 0 is a critical number. If x is equal to 1, again, y equals x cubed. So y is equal to 1 cubed. So y is equal to 1. So when your x is equal to 1, your y is equal to 1. So 1, 1 is another critical number. If x is equal to negative 1, again, y is equal to x cubed. So y is equal to negative 1 cubed. So y is equal to negative 1. So negative 1 comma negative 1 is another critical number. So we have 3 potential places where our local maximums and minimums might occur. We have to test all 3 of these using the second derivative test. First, let me compute the general formula for D. So again, let me have for reference these guys up here. So let me just go ahead and copy and paste these down here. So I need the second derivative with respect to x, second derivative with respect to y, minus the mixed partial squared. We have the first derivative with respect to x, taking the second derivative with respect to x, that's 12x squared. Here's the first derivative with respect to y, taking the second derivative with respect to y, that's 12y squared. Minus, we can use the first derivative with respect to x and take the derivative of this guy with respect to y, so that's negative 4 squared. And there is my general formula for our computation for D. Right, so that's 144 x squared y squared minus 16. At the point 0, 0, the value of your D, 144, 0 squared minus 16, is equal to negative 16. So we have that at 0, 0, you have neither a local max or local min. So no local max, no local min, we have a saddle point. At our next value, 1, 1, let's see what we get. So our D is going to be 144, 1 squared, minus 16. So no need to over compute this. This guy's going to be a positive number. So we for sure have either a local max or a local min. To determine which of these guys we have, we'll look into our second derivative and plug in 1, 1 into that. Our second derivative with respect to x is 12x squared. So 12, 1 squared. So 12 is positive. So when your d is positive and your second derivative with respect to x is positive, we're going to have a local min. And your local min is going to be the value of your function at 1, 1. So we need to compute f of 1, 1. For reference, let me copy and paste what f is. So f of xy is equal to this function. So we're plugging in 1s into these x's and y's. So we have 2 minus 4, that's a negative 2, plus 1, that's a negative 1. So we have a local minimum of negative 1 at 1, 1. Let me set this aside for reference. Cool. And one final point to analyze at negative 1, negative 1. Let's see what d gives us. So again, we have our 144 x squared y squared minus 16. When you put a negative 1 and negative 1 here, when you square them, they become just positive numbers. So it's really 144 minus 16. So again, you have a positive coming out of this. So either we have a local maximum or a local minimum. And to give us the insight of which one it is that we have, we'll look at the second derivative with respect to x and plug in negative 1, negative 1. Again, the second derivative with respect to x was 12x squared. So we'll take our 12x squared and plug in negative 1 in for that x. So 12 negative 1 squared. So again, this gives you a positive 12. So when your d is positive and your second derivative is positive, again, you have a local minimum. And once again, we'll take our function and plug in negative 1 into those x's and y's. And in fact, we get exactly the same thing we got before. Negative 1. So once again, we have a local min of negative 1 at negative 1, negative 1.